So far in class, when we've been talking about feedback and closing the loop on the system, we've been talking about the example that we used in class is this car, say, for example. And we saw that adding feedback to that allowed us to modify the error that was generated in some way. And these notes are posted online under the section on lectures. And then there's a section in the mini lecture section you can read about kind of my interpretation of that. But fundamentally, we were looking at a system, say, want to command 65 miles per hour, and we would generate an error between the commanded or desired and the actual, and then we would feed that into some controller, and that would then feed it into the actual plant or the car, and that would actually be the actual speed coming out of there. And then we would take that actual speed, feed it back, and that would be what we'd use to generate the error. So the error is being generated here. And we saw in class that, and with the lecture notes that are posted online, that this, by generating this, using this error, we could reduce, and using this controller, we could reduce the total amount of error, but it didn't solve all the problems. There was still some error that showed up. There are ways to get over this, and imagine if you're driving down the road and you're looking at your display here, and there's your speedometer, and you've got the gas pedal down here on the floor. Then you can look out the window and you can see the road going by, and you would realize that, hey, I'm going too fast or too slow, and then you would press on the gas. So you'd press on the gas more or less so that you could maintain some speed. The reality is that you're doing a lot more with pressing that gas pedal versus what this controller that we built in class was doing. So in other words, if you were to look at versus time, the throttle angle, as you're driving down the road, you would see that it maybe is constant, and as the road changes slope, you would maybe increase and then you decrease, and so on and so forth. But what you would find is that in general with your application on the throttle, that the throttle angle here was not always proportional to some gain times the error in the speed. All right. Sometimes the throttle angle would be proportional, say, to the change in the air, right? Some K, say D, to the change in the air. So this is now looking at basically the rate of change of the air as opposed to the magnitude of the air. And so these are some common ideas that we're going to explore as we move through the class. But for now, until we have some more sophisticated tools to do this analysis, we're going to stick with just the proportional gain. And you're going to do this same sort of thing for the DC motor. Again, we're going to have the DC motor, which we said was, we derived these equations in class today. And out comes the angular velocity of the motor. And in was applied some voltage. And tomorrow in class, you're going to go ahead and close the loop on that. And we're going to actually command the desired speed, and we're going to use some controller to convert from the error that you generate to the desired voltage to apply to the motor to command the speed. So these errors that we're generating can be thought of in two different ways typically. They get classified in two different manners. One is tracking, and here's a definition for the idea of tracking. Tracking is the ability to follow the reference input as closely as possible when no disturbances are present. So that's basically the situation that I just drew, which is if we have some controller here, and we have the plant, there, and then we have some output, and we feed back this signal, and we want to drive the error. We want to drive it to 0. And we want to do that as the reference input is changing. And so a way to think about this would be to draw t versus, say, the reference and the actual output. And if the reference signal was doing, say, it's constant for a while and then it varies and who knows what it does, so that's the signal R, then we would want Y to track as closely as possible to that, but it might track away here and there but then get closer and then maybe go away and then come back down and so on. But the goal is to always try to have the output be as close as possible to the reference. So for our system in this DC motor model, then we can look at trying to do some first order analysis on that. And the way we could do this is say, all right, well, I know that the way we wrote the block diagram for the equations of motion for the motor was to have k over tau, and then we went ahead and put in an integrator, 1 over s, and that's the angular velocity of the motor coming out. We have to feed back a term that's 1 over tau, feed that in through here with a minus sign. So that represents, and this is, I say, this is the voltage coming in. This represents the differential equations, which were given by omega m dot times tau plus omega m is equal to k VA. But what we'd like to do is generate an error. So what we need to do is feed omega m back, and I can't necessarily, well, I could, but I wouldn't necessarily just subtract off the angular velocity from a voltage. I want to command a reference angular velocity. And so I need some way, sorry, I need a minus sign there, of generating the error and then converting it to a voltage. So by closing the loop on here, generating the error, multiplying by this gain Kp, what we're saying then is that VA is equal to Kp times the error that we generate, which is omega r minus omega m. So in this sense, Kp is at least a unit conversion. But what we're going to see is that it also affects performance. And you're going to see that in your exercise tomorrow in class. But this is a way that we would need to generate an error, because we can't subtract angular velocity from volts, right? We need to essentially generate the error from the desired angular velocity and the actual angular velocity, which is this error that we're generating, right? And then we want to take that error, and the size of that error would then be multiplied by some gain Kp to get volts. So that's at least a unit conversion, but possibly it could also scale the system so that even if I had a small error, if Kp were large, I would apply a large voltage. And we're going to see that this has implications in our ability to track, or really what it tells us is that if we're tracking along here, how close do we get, and then how much do we go over? Do we overshoot? And the example of this is, if we're to think about it, is if we're driving in the car and you see, you're looking at the speedometer and you want to be at 65, but you're actually over here at 55. If you jam on the gas, right, jam pedal to the metal, then now your speed goes way past, over, say, out to 85. And so then you jam off the gas and you jam on the brakes, and then your speed goes way back over here. Right, and so you would end up with some time versus, or you could end up with some time versus speed that looked something like, say, here's the desired 65. You would go way over, way under, way over, way under, way under, but eventually you'd kind of get there. Okay. Whereas if this gain were relatively small, you might not press the gas so much, and you might, you get there, you kind of go over a little bit, oh, you come down, you go back over, you come down, And so now there's a performance part to this error that we're using, and it depends on this gain. So we're going to have to explore that issue, and again, we don't quite have the tools to do that. from the point of view of generating errors for regulation, regulation is thought of as the ability to keep the error small when a reference input is approximately constant in the presence of disturbances. So now we kind of have a slightly different problem, but ultimately they seem similar, but they are slightly different, and I'll show you how that works. In this case, we have omega r. Let's just set it equal to 0, which is good as anything else, as being a constant. And now, when I put this closed-loop system together with this control gain, and I'm doing the same thing, but I want to add in a disturbance, so I have an angular velocity disturbance. That now is feeding into the motor model, which is going to be k over tau, and then that feeds into the integrator, and out comes the angular velocity. That feeds through this 1 over tau part. That feeds back here with a minus sign. Then now we're going to generate the feedback all the way out here and put a minus sign in. And so now this is the plant. If I draw a box around that, that's the motor that we're worried about. And so if I write down the differential equations that are generated from this block diagram, what I see is I get tau times omega m dot plus omega m is equal to k times VA, but this is VA right here, all right? And here's the error that we're generating. And so VA is now going to be, and notice it's with reference to a constant, which in this case is 0. VA is now equal to Kp times the error, which is just minus omega m, plus omega d. So when I plug everything in, I get tau omega m dot plus omega m is equal to k times kp times minus omega m plus k times omega d. Collecting terms, I get tau omega m dot plus 1 plus k kp omega m is equal to k omega d. So now k, so omega d here is really kind of being thought of as the input to the system, right? But notice kp never shows up on that side. So our choice of gain over here, kp, really doesn't impact the magnitude of how the disturbance shows up in this system. So this is an example of a controller which actually doesn't help with regulation. Right? This controller, what you'll see tomorrow is it can help with the tracking problem. You'll see that, right? And because notice Kp is multiplied by, if we go ahead and write this all out, we have tau omega m dot plus 1 plus k kp omega m is equal to k kp times omega r. So in this case, in the tracking problem, then kp actually is, and omega r can conspire to generate some sort of change in the system as an input, whereas here in the regulation problem, omega d is just sitting off here by itself times k, and our choice of kp doesn't impact the system. So our choice of control law here, or controller, is really going to impact our ability to track or regulate various systems. And in either case, generating this error as either a regulation or a tracking error ends up being a useful construct. So really what we're talking about here is if I look at plotting t versus omega m, and I'm trying to regulate down to 0, in the presence of this disturbance, the system might start out at 0, and then depending on the disturbance, it might kind of wander around, but it might end up going to some constant offset value. But I have no real way of measuring that because it's not showing up in the error that I'm trying to generate. It's just showing up as this disturbance being added in as some sort of steady offset.